This information is brought to you by Charles Sturt University.
Now it has. Well, welcome everybody. So we're continuing looking at graph theory, and so today I'll look at trees in particular, last week, and also weighted graphs and some algorithms you can do on them. So trees were already mentioned. So a tree pretty much is a graph which is connected and acyclic. If we have a graph that's acyclic only but not connected, then that's pretty much a disjoint union of several trees, and so therefore we call it a forest. And so the fact that acyclic means there's no loops. It also has lots of strong properties about it, and therefore they're useful in many data sort of structures. So things like a priority queue and various sorting algorithms are usefully done using trees, which I'll show to you in a second. They're also created when you're doing parsing computer programs, for example. So the parser will create a tree, implicitly at least, of what the whole program looks like. So they crop up in various sort of forms. So they're sort of useful things. So let's look at some properties, things that are special about them. Get my phone off there. So a tree's a planar graph, and so therefore the Euler characteristic is 2. And the Euler characteristic we did from last week was the number of vertices minus number of edges plus number of faces equals 2. Now there's no cycles at all. So if you ever draw a tree, there's no little loops anywhere. So therefore there's only got to be one face, just the outside face. So we know that f is 1. So by plugging in an equation, we quickly get that the number of edges is 1 less than the number of vertices. You can say it other ways. So there's a very strict condition on the relationship between number of edges and number of vertices. And so you basically get a tree, start with a node somewhere, and then you just from that one node you just draw edges, the other vertices gradually. That's how you create them. And so therefore, when trying to work at trees, there's a clear relationship between edges and vertices. So some other special properties. If you pick any two vertices in a tree, there's one unique path connecting both of them, and it's a simple path, meaning there's no loops around, no doubling back sort of thing. So that every single two vertices are always joined by a unique path. And the reason is because there's not much choices. There's no cycles in there. There's no loops to go around, and because it's connected, all 2 points will always be connected. And so, as a consequence of that, because there's always a unique path between any 2 points, if you add another edge there, that creates a cycle. There's already a path in existence, and the edge just creates a cycle. And so, on the other hand, if you start taking away edges, it basically allows you not to have that unique path anymore, just means things are not connected. So adding paths stuffs up the acyclic nature, destroying edges makes it not connected anymore. And so it's really that fine balance between those two sort of properties. So pretty useful stuff. So one thing that's useful for any graph is called a spanning tree. And I'll do an algorithm later on how to work out the minimal spanning tree in a weighted graph, which is a useful application. So you've got any old graph. A spanning tree pretty much is a subset of all the edges of the original graph, so that those subset of edges form a tree. But more than that, that tree must counter all the vertices of the original graph. So let's look at an example. So this is a graph. So what I want to find a spanning tree for this. So I've got to basically, it's not a tree at the moment. Why is it not a tree at the moment?
It's got a cycle.
Because it's got a cycle in it. So pretty much I need to choose some of the edges from this. So I can't use them all, but some of these edges to make and just a tree structure. So I need to make sure I include all the vertices. So if you think of this vertex here, for example, the only way that's going to be connected to everything else is if I hang clear that edge. Otherwise, that one edge will be disconnected and won't be a tree. Similarly, this one here, to be connected to the rest of the vertices, must include that edge. Otherwise, it would be disconnected. So those two edges must be included in a spanning tree, otherwise it just wouldn't connect to everything. For the other three edges there, I don't need them all, because there's a cycle. Which ones would you pick?
We just need one of the following two from that.
Okay, so let's just pick one of them. So we should pick this one, for example. That connects those four vertices that it passes through, but the last one isn't included yet. So it's still disconnected. So I'll still need at least one more edge to connect to that. Which one I'll pick? Doesn't really matter. So I could pick that one. That's one choice. So that would be a spanning tree. So it's a tree, as in there's no cycles anymore. We've got rid of cycles. And it does connect all the vertices together. So that's a spanning tree. That's not the only option. So another choice would be the first two are forced, but you could have picked, say, that one and that one would be a different spanning tree. Or that one, this and this. So those edges, which is non-isomorphic, would be another spanning tree. So there end up being three choices in this case. So spanning trees may not be unique. There might be several available to us. And so what it comes down to in a given application, which one would be most care about? And so when we start putting weights, numbers on them, then you might go, well, which one is more desirable to us? So we'll have an algorithm for finding the best spanning tree in a second. But you can see there's lots of them present. So every connected graph has a spanning tree, at least one, maybe quite possibly several. Anyone who's had to prove that's actually true?
Math.
More information, please.
Maths. Ness.
So look here, this is an arbitrary graph. So pretty much, if you get any old graph, if it's already a tree, then the graph spans itself and you're done. That's the easiest case. Otherwise, it's not a tree yet. We're assuming it's connected. So I've got a connected graph. And if it's not a tree, let's assume it's not a tree. So if it's not connected, so if it is connected but not a tree, that means it's got a cycle in there somewhere, like this one does. So you can see there's a cycle here. So if you've got a cycle, then you can just safely delete one of the edges and it will still remain connected. So this is the cycle that we've got. So I'll leave all the other ones there. So that's they're the non-edges not involved in the cycle. So those three edges involved in the cycle, I can just delete one of those and the graph would stay connected. So let's just pick these two. So what I've done here is I've deleted this last edge here effectively. So if you've got a cycle, you just delete one of the edges, and that because there's the rest of the cycle, it will remain things connected. And so you can always keep deleting edges like that. So if there's any cycles left, you can always delete one more edge to get rid of the cycles. And you can keep going until there are no more cycles left. So looking at this last case here, there are no more cycles left. We got rid of the last one. And so if there's no more cycles, it must be acyclic. It's still connected. And since it's acyclic and connected, it must be a tree. And you can see this is one of the spanning trees we had a second ago. But the same argument applies to any sort of graph. You always just delete edges to get rid of all the cycles, and bang, you've got your spanning tree. What choices you make, you get different ones, of course. So spanning trees always exist, and we'll look at ways of finding the best one in a second. Okay, so often applications that we're concerned about are what's called rooted trees. So these are trees where we pick one of the nodes to be the root of the tree, and everything else grows from that, is the metaphor. That's a picture. So normally we actually write them upside down to what you think trees in real life do. So instead of growing up out of the ground, going down.
Well, it'd certainly look a bit weird if you flip that upside down. Wouldn't really look like a tree anymore. It'd look like a spotlight or something.
A shrub, like a tree.
A shrub.
Yeah.
So trees just go like that, do they? That's
Like, you got like the tree trunk and you got everything else.
Yeah.
But that doesn't go like that.
So
if you style a tree like that.
So this is a tree. So the root of the tree in this case is A. They normally draw the root at the top. Everything else comes down.
Christmas tree. Christmas tree.
So they use different names. So the common way of naming the different nodes or vertices is in terms of family names. So we think of the oldest person being at the top and then going down. So A is the parent of B, C, and D. Is the word we would use. So, and you can use other words. Let's pick what do you reckon? What are the children of A?
They just be B, C, and D.
So they're the children. A is the parent. The other one then is the children. What's the parent of G?
C.
C. What are the ancestors of G?
C.
A and C. So an ancestor is parent or parents of, etc. So parents of recursively. What are the descendants of A?
Everything else.
Okay, everything else.
C,
Right.
D, E, F, G, H, I.
Good job, David.
Everything else would have been sufficient. So you just did normal words. So very commonly we talk about parents and children. That's a very common word when talking about trees. But other words are also useful. So just the normal. So trees, rooted trees are very common. So you see them in file structures, organisation diagrams. This is one from CSU, for example. Table of contents is a rooted tree. Knocking competitions, you can pick lots of them. So so a table of contents, you have the root node is the book itself. The first level of children would be the chapters. The next levels would be the sections within the chapters. That's the idea of a table of contents. So they're very common ways of doing stuff. So I want to look at one in particular before we get to another example. That's called a binary tree. So a binary tree where each parent has at most 2 children. So in the last case, A there had 3 children, so that's not a binary tree. So looking at binary ones, they have at most 2 children. Furthermore, we have a full binary tree if each parent has exactly 2 children, none at all. So in this case, A has 2 kids, B and C have 2 kids, D, E, F and G are sort of terminal nodes. That's sort of nice. Full binary tree, and it's nice and balanced as well. So every single row is completely full. And so we can use binary trees for various things. So they're often used for nice sorting algorithms. So a binary search tree, for example, is a way of sorting out data. It works most efficiently if it's balanced and full, like this one is here. So if they're unbalanced or they're not full, it means you tend to slow the whole process down. So algorithms which make these things in a balanced fashion end up being better in the long run. I'll touch on some of these things in a second. So binary tree really just means every parent has most 2 kids. Okay, so we often have a bunch of nodes here. We want to try to give a nice order to these things. So there are different ways of ordering the different vertices within a tree structure like this. These are 3 common ones. I'll mention a 4th one in a second. They all have different uses, and I'll show you some applications for them all, why they're useful. So an in-order traversal. So these are just different ways of looping through a tree. Maybe you want to think of it that way. So you've got a list. You can loop through a list either going from the beginning to the end or end to the beginning. They're the two choices, really. Not much to choose from. Here with a tree, you've got lots more different ways of doing it. So an in-order traversal basically means you do the left, and then the parent, and then the right. Let's show you what they would look like.
It's pretty rough, eh?
So in order, basically, we're starting with the root nodes, so we're up here. So at that point in time, we do the left, and then the parent, and then the right. So the in order means you do the parent in the middle of the left and right. So you always do left before right, that's pretty much always universal. And then you're doing the parent in the middle of it, that's what the in stands for. So first of all, A, you don't do A, you want to keep going left. Start going left. With B, a B again is a parent of other children. So it would go left first, it would go to its left child first. And then with D, it does its left children first, and there isn't any, so it just ignores them. Then it does itself, because it's in the middle. And then it will do its right children, which are none of. Then it goes back up. So D's the first letter would print out, so to speak. Then back to B. B's already done its left, now it does itself. And then it goes to its right children. And so then E's by itself, so you just do E. And then you head back, and head back. So what's the next one in order? A? So you can go, what's the next one? F. So I'll go all the way up to C, do its children first, so let's try first to give F. And then then C, and lastly G. So that's doing an in-order traversal.
If your parents have to be dead.
So we can do other ones. So I'll just do other ones. So pre-order is another way of traversing it. That's basically doing the parent first, then the left, then the right. So pre-order is a common search technique. So if you're trying to, so other applications of a tree. Guys, can be quiet for a sec. An application for a tree would be the all the possible moves in the game, whether they be chess, which there's lots of options as you can imagine, or noughts and crosses. So
How many options are there in chess?
Billions.
too many to want to enumerate them all. But even if you want to just think about the moves, so you've got the computer player. Any player has most 16 pieces on the board. So the root node would be, okay, it's more your turn. All the children of that would be the 16 different pieces that you can move. And each of those would be all the different options you consider. Now, so that's the sort of logic behind it all.
That's a lot.
Now, you're going, well, which node would I want to go through first? So in practice, when you're trying to work out what your next move is, you're not going to consider all options. The computer doesn't do that. You will just go, I want to just explore some parts of the tree to work out what my next move is. So the different way, so doing a different traversals gives priorities to different nodes. So an in-order is one way, which doesn't really work well for a game tree. A pre-order is a bad one, as I'll show in a second. Well, would not be very good for chess. But so a pre-order traversal does the parent, then the left and the right. So what's the very first thing you would do in a pre-order traversal? A. So it starts at the bottom.
No, we're here.
What would it do next?
B.
So go left and do B.
And then you go D and then E.
And do D and then E. So this type of traversal is called a depth first. So depth first. So a depth first traversal pretty much just goes deep into the tree first off. So you can see the first three are going all the way to the as deep as you possibly can straight away. That's what's called depth first. So if you had lots more layers, it'd just keep going deep and deep and deep. So looking at the details, essentially, in the game tree. Where sometimes in games you don't want to do that, because it means you're spending all your computation time on one very small aspect. So moving your pawn, all the different locations of moving pawns, which may not be that very good for deciding what to do. So we'll look at different searches that might be more useful. So that's the first three moves of the depth first. What would come after the D?
Maybe
E. Yep.
Then you go C, F, G.
Then goes C, and then F, and then G. Everyone okay with that? And you can do a post order, same sort of idea. You do left, then right, and then the parent last. That's a post order. So in order, pre-order and post order are the sort of common ones. You have a binary tree. So the other sorts of another common one is called a breadth first search. That's where you basically go. So breadth first is when you go through the layers first. So you do the first layer. So what's the first layer?
A.
Just A. Then you do the next layer from left to right.
B, C, A, B, C.
And the next one?
D, E.
Yeah. So a breadth first just goes along the layers from left to right. Breadth first.
Breath or breath?
And so what that's used for a game tree is looking at the bigger picture first, looking at all its options before it, and considering all of them in some degree before getting more detail. And so in a game of chess, when you're going to run out of time to do the computation, getting the bigger picture first is one idea, for example. Yep.
Is it breath or breadth?
Breadth is in width.
So
you
not breath as you've written.
Yeah,
Sorry,
yeah.
I was confused.
Breadth.
For that.
Cheers. So these are different sort of ways of traversing a tree. So you're going, well, let's see some applications of them all. Okay. So one example of where you see trees is when you're doing parsing code. And so one particular aspect of parsing would be parsing mathematical expressions. Like in Java, C, Python, all of them basically have to read the expressions you have and convert them in a way that can actually do some calculations for them. So that's one expression in the middle of the slide there. So A minus B on C times D plus E. So in order to evaluate it, it has to first understand what you've written on a piece of paper, essentially. What it does implicitly, rather than explicitly normally, is it creates a tree structure that corresponds to that. And so as it reads through the tokens of your line, so it breaks the line into tokens, and it converts implicitly a tree structure. So, let's copy this thing out. So how it works is it works out the operation you do last in the calculation and makes that the root. So doing that expression, what's the last operation you do? The multiplication. Yeah. So the first thing you do, if you remember from school, is bid mass. So the first thing you do is the brackets. So you do the brackets first. Indices, division, multiplication, addition, subtraction. So you do the brackets first. So in this case, you do everything in the brackets first and multiplication last. So multiplication is the last thing you do. And then from the multiplication, its children would be correspond to each part to try to multiply. So the thing on the left here would be the A minus B on C, for example. So A minus B on C, you're doing two operations. You're doing a minus and a division, you're doing both of them. Which one would you do last of those two? The subtraction, because the division has higher order of precedence. So you do the subtraction last. So its left would be A, its right would be B on C. So how would you write that down? So you do, it's the division operator, you're dividing B by C. On the other side, so the right of this multiplication is d plus e, and so it'd be plus sign, and its children would be d and e.
That's an interesting one.
So that's called an expression tree.
Really express yourself.
Problem solved.
That's the answer.
That'd be a lot of
Write
emotions for a
it down in the test.
Hmm?
Full marks for it. But like, what's the answer to this? And you're like, just write down that tree.
Okay, so it creates it as it's going through, and so the benefit of expression tree is it doesn't you lose the brackets, so you drop the brackets out. That's one thing. You can do lots of things with them, but let's just do a few stuff. Let's do a in order traversal of this sort of one here. What's an in order would look like? So in order means you do your left, then your parent, and then your right. So left, parent, right. So you do the parent in the middle of it. That's what the in order means.
Start with A.
So you keep going left. The first leftmost thing you get is A. Then you move up.
You get minus.
Minus.
Then you get division.
No, so you're going all the way down to A, back up to a parent, so you head to the right.
Oh yeah.
Then you keep doing its left first.
Oh, B, yeah.
You do the B
C.
divided by C.
And then D.
So you get No, you get multiplication.
Oh.
And then you get D plus E.
Yep. Yeah, everyone okay with that?
Easy.
So for each individual section, you're always heading to the left. Go as far left as you can first, and then you backtrack to the parent. You go right.
Yeah, that brackets.
So what's the difference between that and the original expression?
Brackets messed everything
It's lost the brackets. So what you would normally do, you wouldn't print out the expression. You would only evaluate it. That's actually how it evaluates it. So you'd actually that's the evaluation of it effectively. And when you evaluate it, it would do the D plus E first before it actually combine it with anything else. So that's really effectively how you're evaluating the expression tree. You can see though that an in-order traversal doesn't work unless you start putting brackets in. It would fail otherwise. So what computers often do is not do that. They often do other sorts of traversals. This is called a post order. So we'll do a post order and then explain what we're getting from it. What's the post order traversal? So post order means you do left and then right, and then you do the parent at the end. Post means afterwards. So you hit going all the way to the left, so you start.
A,
So it's A.
then B,
Yep.
then C,
Division, then
Then division. Yep.
subtraction.
Then subtraction.
Then we'd go D, and then E, then plus, and then multiplication.
Okay. That's called a post order traversal. So let's give some names to what we've done here. But leaving out what the end there is
Reverse
easier for a computer to deal with than the one at the top.
Uh,
So this top one with the brackets is called infix notation. That's what we utilise. We write down maths on a piece of paper. That's what we normally do. This one here is called postfix.
first college.
Yeah, that one.
Yep.
We did that in one.
Yeah, I did not.
very bad.
I didn't understand that at all.
I hated it.
So it's reverse Polish. That's right.
That doesn't look like regular Polish. That can be reversed.
What's regular Polish?
Probably with the
Isn't it just
thing in
infix
the
what
right.
we use?
It's a pre-order. So a pre-order transversal gives a Polish notation, which looks similar to that.
So how do they do maths in Poland?
Yes.
Oh, yeah.
Why is it called that? It's because
Guy.
a Polish guy came up with a way of doing prefix notation for logic expressions, like what we did in topic 1. So and
then he did it
or.
backwards.
And then
And
started
then
Polish
he did it
was
backwards.
open up, so it became everything but Polish.
Oh, I don't know. I don't know why who decided reverse Polish.
And he was like, I want to use my name on this. So what the Polish way of doing it?
Okay, so where does postfix notation ever come up? I mean, we don't see it naturally because we just write infix all the time. Anything else? Do you know anything in PostScript notation?
Probably something.
PostScript does.
That's how your calculator does it.
Yeah, that's how your calculator does it. So older calculators, it's older than all of yours, I'm sure. So sometimes
Probably
provide that.
How those cheap $2 calculators work.
Oh look, you know your phone, the technology in a phone far surpasses all those. It's pretty cheap to make even pretty good calculator now. But so that's how basically how calculators often work is converting implicitly into that sort of notation to evaluate things. How it works, let's get one of them. So the this in-order traversal, what it produces doesn't produce the brackets, would fail because the brackets are important when how we write it down. Quite again, guys. So this polish, reverse polish, or in polish is similar, doesn't really require you to have any order of operations. You don't have to worry about that. You don't have to write brackets. It all just takes care of the notation itself. So how it works is you have effectively have a stack. Do you know what a stack is? Yeah.
That's a pen stacked on a piece of paper.
Oh my god.
So you have different. So you have different starter structures. So stacking is first in, last out. So a queue is first in, first out. So the first thing you put in is the first thing coming out. So push it at one end, it comes out the other. That's what a queue is. So a stack is first in, last out. So with a stack, so the first thing you do is when you see a number, like A in this case, you just put it on the stack. And when you see any number, you just keep putting it on the stack.
Also, like,
It just builds up.
Yeah.
So you see the A, you put A on the stack. When you see the B, you put the B on the stack. So it goes up. When you put the C, it goes A, B, C. So you just keep building the stack up. When you get an operation, like divide,
chuck that.
it would pop the top two elements off the top of the stack, so B and C in this case, and apply the operation to those. So we'll do the B divided by C. Gets the result and pushes it back on top of the stack. So after that, have A and then have the result from B divided by C onto the stack.
Minus, yeah.
Then the next one is minus, so it pops the top two numbers off, does the operation, and then pushes it back on top of the stack. So it'd be A minus B on C. So it'd be a number, of course. Then the next thing he gets is the D. So it pushes that on top of the stack. Then E pushes that on top of the stack. Then with the plus, pops the top two entries off, applies the operation, and then pushes the result back on. So A minus B on C, and it would be D plus E on top of the stack. Then for the multiplication, pops the two off, multiplies them together, and pushes it back on the stack. And once you get to the end, it just pops the stack, and that would be the answer.
Yeah, that makes sense.
That's pretty much how it works. So using stacks is sort of the key idea.
The publish guy was pretty smart.
So often when any coding you do, the computer uses stacks for that as well. So when you're writing functions in a computer language, every time you enter a new function, it basically pushes that onto a stack of where you're up to, etc. And when you exit the function, you reduce the stack down. Did you do that in ITC 161?
We just had a question on the postfix notation or whatever. It was just in one of our assessments.
Yeah, it wasn't really gone over in depth.
No,
Could you do that?
we heard about it.
Assessment and final exam.
We heard about it, and that was it.
So for me, it's an application of a post-order transversal, which is useful for other things, but just showing you where it's useful. So a prefix notation, which is normal Polish, is in Lisp, which is a computer language. Not heaps common in Italy, but people who write Crash Bandicoot and other things.
Oh my god.
They wrote that in Lisp.
Crash Bandicoot.
Oh, the original ones were written in Lisp, which is pretty impressive. Considering
It's
that.
older than you, David. My Crash Bandicoot is older than me.
I think it was. I'm not sure. I'm not sure if the variant they used actually had the had all the prefix notation for their arithmetic, or they had an adaptation for it. I'm not sure. But Lisp, in the original version of Lisp, there are variants of it. Has everything, including functions in prefix notation. Has absolutely everything. So, okay. So that's one application of just tree traversals. So expression trees are binary trees, and you can do them to work out. In truth, in computers, they're not 100% accurate because they've got random errors, and you can use those expression trees to estimate the amount of errors, etc. as well. But that's another subject. So another sort of thing, another data structure that's common is a binary search tree. So these are pretty much a binary tree where we add elements in a way that keeps some sort of order to them. So pretty much how it works is you start with an empty tree, so the roots, there's nothing at the end yet, so it's pretty much all empty. And you have so when you want to add an element, if there's nothing there at all, you just make a new one up. So it might be easy just to do practice. Okay, let's just do an example. Okay. So I've got a bunch of letters. The order you add them in makes a difference, which I'll mention more in a second. So the first thing you do is we've got no tree at all, so I haven't drawn anything. The very first node you get, you make that to be the root. So J is going to be our root. So that's that one done. To add a new letter, the next letter is N, or it would be some sort of value, doesn't have to be strings. You compare it with your current node. Now, if it's less than, you make it to put them to the left. If it's greater than, you go to the right. So is N less than or greater than?
What context? Like position?
In alphabetical order.
It's afterwards, so it's to the right.
Greater.
So we're going to put it to the right. If there's nothing there yet, we just insert it at that point in time. Otherwise, we just keep recursively going, which I'll explain more in a second. What about H? So you compare the root node, which is J, left. So you go left. There's nothing there yet, so we create a new node with a value of H at that point in time. So the next one gets interesting. So we're going to look at K. K would be left or right? Right. Then with N, there's something there, so we have to make another decision.
The left.
We go left. Give you K. So with D,
All the way to the right.
you go right, and then right again.
Left.
So left again, thank you.
And then right.
And the last one, L.
Right.
So you go right,
And right.
and then left, and right.
Basically, it's the start of a bird's legs.
For what?
It's missing its left shin. And then you got a set of bird legs.
Okay.
I see it.
Can you insert an E in there, actually? That'd be really cool.
Right.
And then we'll have bird legs.
So where would an E go?
Better go on the right of the D.
Yeah, go in the right side of the D if you want to do that. So before I do that though,
Oh, come on.
is-
It'll be amusing.
Bird legs.
I'll see what you're going for, but
what's an in-order traversal of that particular tree? So in-order means you go far left as you can, then you do the parent, and then it's a left, parent, right all the time. So what's the in-order traversal? What's the leftmost thing?
D, H, J, L, K.
So D, H,
J.
J,
K.
K, even. You do the parent before the right child.
Oh, yeah.
L.
So it'd be K, and then L,
And then N.
and then N.
Because favoritism.
What do you notice about that?
It's alphabetical.
It's alphabetical order. So that's basically a way of sorting out data. So one way of sorting data doesn't have to be, it can be numbers, it doesn't have to be strings.
Very very extensive way to sort data.
So it's got a binary sort.
I love the H. That's my favourite one.
I know binary sort's not tree binary sort. Made a lot more sense before we did this. A binary sort.
So, this particular sorting is not the best way of doing it, depending on, because it's very highly dependent on how you add the nodes to the tree. It works most efficiently when it's a very balanced tree you get. So this one's not that balanced. So,
Shin still, so you know.
H though.
Yeah, it's an M.
It's a backwards end.
so you could refactor. You could just rotate, so to speak, elements of the tree so that KLN you could rotate to be KLN. You can rotate elements of the tree in a certain sort of fashion. That makes a more balanced tree, which means that's more efficient. So what you can do is binary search trees are a way of sorting out data. If you get them elements in pretty much a random order, then you get close to a balanced tree, and they are a useful way of sorting out data. They really are, despite your misconceptions, despite your doubts. It is quicker than a selection sort, for example. So they do have benefits to it all. But the downside is if you don't have such a random order, you might get quite unbalanced trees. And so there are algorithms in place that automatically balance the tree for you as you're going along. So they're called self-balancing binary trees. And they will do things like rotating elements as they need to. As if the depth's getting too big, they'll just rebalance it to make it not so big. That's at least how they work. And they are one useful way of storing information. So if you're trying to... so binary tree is an example of a prefix tree where you just... looking at it. So they are useful mechanisms for storing all sorts of data in sort of ordered fashions. And so often the pain is getting them in the first place, but then you can read them. So you could put this on a hard disk, so to speak, and this would store all the information for you. So you could store a whole dictionary in a sort of format like this. The most efficient in terms of capacity, space, like in terms of that sort of stuff, is a ternary tree we have, and just 3 children per parent. They're just harder to program. So someone might just go binary trees, they're easy to program.
I just said, what if you got two are the same?
So, like, say you're doing a spell checker, it doesn't need to know duplicates, right? So it only have one word. So you'd have a whole dictionary of all different unique words.
Yeah, I'm not talking dictionary-wise. Like, say you have a tree of data.
Yep.
And you got a duplicate of something. Like, say you have 2 files the exact same, or two words the exact same. How would you store them in the tree?
Chuck them on. Just put them left.
So just to the left again.
So if you had another D here, for example, I'd make it the left child of D.
Right. So then you're starting to put a little bit early and it's missing half a leg. It's the full.
So basically, the left will be less than or equal to.
Right.
We have duplicates, and again, you need to have that sometimes. Absolutely. Okay, so in terms of data structures, good way of how to represent these. Basically, the way to represent a binary tree really is just to have a data structure for each node, and so you have the data structure for the tree really is just the root node, and each node itself. So the root node in this case would be the first one up top here, and so that node would have a value it contains, in this case a string effectively, and then it would have links to its 2 children. And in using the sort of C notation, zeros represent a null pointer, numbers represent pointing to the data structure. So you're doing Java at the moment mostly, aren't you?
Java 1.
So how would you code that up in Java?
With Java.
Okay.
Because we're doing this subject, doesn't mean we know how to do
Yeah.
the subject.
So basically,
I'm just a bit confused. Just
I'll just use a 4-dimensional array. It'll take me a while.
you have to have nodes. It's a class in Java. So essentially, the class is just all your data types. So you've got to have the value and its left and right children. So you can say there's the value and it's left and right. That's certainly, and again, they'd be defaulted to null pointers to begin with.
Sorry.
You're right?
Yeah.
And so that's the nodes themselves, and you still need a data structure for the tree.
It's just
What would the data structure for the tree look like? What would be its variables?
sorry. What?
What would be the variable? So if you have a class
What would
called
the
binary tree,
value be?
so so this is the class for the nodes.
Yeah.
So that effectively in my picture, they're the individual lines here. What would the data? So you're going to have another class called binary tree. What would its variables be?
I don't know why you'd need a binary tree class too, because the first node is the start of the tree and it holds all the others within it.
So that's pretty much it, right? So you just need a root.
Yeah.
So because you want to have, in object-oriented stuff, you want to have, basically you don't want to reveal your implementation for stuff to the users necessarily all the time, whether it be other systems. So essentially you're keeping all that abstracted away. So yes, you could program it so you're just dealing with the root node directly, but often it's easy to have all those functions in one class by itself. Encapsulation, isn't it? Do you use that word you used? I'm using it properly. So, I mean, that's how it looked like in memory, effectively, but how you code them up in terms of object-oriented stuff, essentially is just the different variable in a class structure. So the class defines that data structure. Okay. Sort of things I want to look at are called weighted graphs. So a weighted graph pretty much is a graph where you assign a number to each edge. Here's an example one. So these are the different nodes are places in Sydney, and the weightings correspond to the time or distance, effectively, so the distance between the different locations in Sydney. So weighting just really means you're putting numbers on each edge.
What is this traffic though?
Yeah, and so in truth, you might have variable weightings that change depending on time of day, etc.
In Sydney, I don't know. There's not much traffic in Sydney.
You obviously haven't been there.
Oh no, I've never been there.
No, never.
Much.
Never.
Whoa!
Definitely haven't been there during.
So
lockdown.
there are
Why are we learning now about drug sales and
pharmaceuticals.
like
Christian doesn't author one.
the drug rep, the travelling salesman wants to visit every pharmacy trying to sell his new drug. This could not sound any more sus.
He's like it's
If
blue.
you tried.
I also teach pharmacy students, not this subject, but I teach them else. So, and drug reps coming and trying to sell you stuff.
Do they use
It's door-to-door coaching
Depends
sales.
if you run a franchise or not.
I've never heard of a door-to-door drug
I
salesman.
can see it happening in Sydney.
I've heard of a door-to-door Jesus salesman, but that's a bit different.
Did you buy?
They don't go to your door; they go to the pharmacy's door.
They go to
Anyway.
the door in the back alley.
So the first sort of problem, there's quite a few different problems that you can consider for weighted graphs. I'll look at some of them. The first one is the hardest of them, which we'll do the least on. It's called the travelling salesman problem. So imagine there's a salesman, so a pharmaceutical rep, essentially, who comes from the city.
No, Parramatta's not up there.
And they basically, what they want to do is they want to visit pharmacies in the other 4 locations and then come back to where their head office is at the end of the day.
Pharmacies.
Where's their head office?
City, in the city.
That's terrible. They'd be paying rent on the roof. Like,
Yeah, but
they make enough sales to afford that.
Oh, you don't know what they're selling.
Okay, you can choose anywhere else if you wanted to, but the answer being the same regardless where you want to start from, to the truth. So we'll start the city, and so what I want to do is they want to visit everywhere else, and then come back to the one. So what they want to do is they want to have a cycle which passes through all the nodes and comes back to the beginning. So that's called a Hamiltonian cycle. So we looked at Euler cycles. What's an Euler cycle again?
You can go around all the things like once.
Euler cycle means you're visiting every edge exactly once.
You don't want to do that, though.
We want a Hamiltonian cycle, which is different. We want to visit every node exactly once and come back to where we started. So that's the difference. So Euler cycles, easier to find. Hamiltonian cycles, a bit more complicated. More importantly, though, there's lots of them. And what we want to know is, he wants to get down around as quickly as possible, so he wants to have the one which has the cheapest cost. If you add the weights along the path, Hamiltonian cycle he's picking from, this pharmaceutical rep would like the one that has the lowest total weight.
So he needs to end back at the city. He needs to end back at the city.
Yeah. So he wants to start in the city, do a go a bunch of edges and finish back in the city again. So, for smaller cases like this one, you could do a brute force, which basically means you consider all possible paths and you just add up the sum for each path and work out which one's the lowest cost. So it gives you the exact value. In this case, a computer could do this quite quickly because it really is a pretty small case. But even when you get up to about 20, that approach starts slowing the computer down. Because the number of options grows quite quickly. So this is a hard problem. Actually, a fancy name. It's called an NP hard problem. So NP, I'll show what it looks like.
No problem.
Here it is, NP hard. I don't have a hard time explaining it all, but N stands for non-deterministic polynomial time. Hard. So the easier problems are can be done in polynomial time, which I'll explain more next week. The next sort of class ones are easy to check in polynomial time. They're called, which is NP problems effectively. NP hard problems are ones that are at least as hard as those sort of problems, probably harder. So it's basically it's a very fancy way of saying it's going to take a long time to try to probe it directly. So when it gets to bigger networks, the best thing to do normally is either get lots of computers to try to do it for you, or a better thing is just to be satisfied by a close answer rather than the exact answer.
Well, that's silly.
So an example of this case, one rough way of doing it, a heuristic method, is just to pick your closest city each time, closest location. So if you start at city, which one's the quickest location to get to first? Granville. So let's just go to Granville first. That's called a greedy algorithm, because you're just basically picking the cheapest one straight away and don't care about what happens later on.
Horrible way to do things.
So basically, if you get stabbed in Penrith, you're screwed anyway. Don't worry.
So greedy algorithms sometimes work, not in this case necessarily though. But so you go to Granville, which one would you pick next? Which is the max? From Granville, which is the cheapest to go? Liverpool on 12. Then you're in Liverpool, which is the cheapest to go then.
Parramatta.
So up to Parramatta. Then from Parramatta, Penrith, because that's the only place you haven't been to yet. Once you're in Penrith, you have to go home, back to the city. So that's sort of the closest neighbour approach. It's just a heuristic. So if you did that, you get a value of 109 if you add up all the weights along those stages. Now, if you do a bit of mucking around, you can actually, by trying all the options, you can realise that the cheapest option happens to be a different path to that.
You just go in circles.
Which might make sense for other reasons. And so these heuristic methods may not always give you the best answer, but hopefully they're close. So is 109 close to 101? You'll be the judge. But so that's basically how the travelling salesman problem works, is that for small problems they just try to do it directly, maybe using parallel computers to try to save it up. or if it's a bigger problem, they use heuristics to get an answer that's close to it. People do this sort of travelling salesman problem all the time. So an example of someone I knew from uni, what they were trying to do, they were having a helicopter flying, this is the defence forces, flying over ships to check out what they're containing and come back to the main ship. And they want to do it to use the least fuel on the helicopter as possible. Which is a travelling sales problem. The difficulty they had was that ships don't stay still and they move around for you. And so it's basically a moving travelling salesman problem. But that's something they were trying to defend for. So it's a well-studied problem. So just to show you what some will do with brute force. So a few years ago, someone had a graph. I can't remember what it was corresponded to. So which had a lot of points. So 86,000 different nodes in a graph. And then they basically solved the travelling salesman problem using brute force, effectively, by trying all the different options, hopefully in a smart way and using parallel processing. They didn't use just one computer. Yep.
What does CPU use?
So basically, if they ran the same code on one computer, it would have taken that computer 136 years to solve it. They didn't use one computer; they used lots of them.
Why not just employ Google for 3 minutes and just do it then? Well,
that's what they did. So they basically just ran it in lots of parallel computers, just parallel processing.
I'd say you could just employ Google for 3 minutes, if that. Google has that much processing power.
So the difficulty is trying to get the parallel processing working well, which Google has APIs to do that immediately. So
Google's the master at it.
So that's one problem. That's a hard one. Let's look at some easy ones we can actually try to do directly. One's called a minimal spanning tree. So as I mentioned before, minimal spanning trees. So if you have a weighted graph, you can give values to different spanning trees. So the cost of a spanning tree would be just adding up the weights of that spanning tree. So we would like to find the one that's the cheapest, essentially. And this one's much more doable problem. So this is not a hard one. This is a good one. So this is an example of an engineer trying to connect different things together. So A, B, C, D, E, F are different locations. And he's estimated the cost to connect the different nodes together. So A to C would cost 1 unit, and D and F would cost 2, for example. So he doesn't need to connect everything directly. So one way of connecting A to D, for example, would be to have A to C, then C to F, and F to D. That would be a sufficient way of connecting A to D together. So long as their path between them, they're connected. So in that case, all that he really needs to do is have a spanning tree, because a spanning tree will connect all the nodes, and spanning tree is automatically the best because it connects them all without any cycle. It doesn't have any extraneous edges to it. So we want a spanning tree, and he wants to know one that's the cheapest of all the possible spanning trees in this. And because there's a few cycles, there's several spanning trees available. We've got to work out which is the best one. So that's pretty much the problem. And again, in your assignment, there's a spanning tree problem. So in assignment 3, there's a minimal spanning tree problem. So there are several different algorithms to do it. So the two simple ones are named after the people. So Prim's, I feel it's named after several people. I can't remember off the top of my head. So Prim's algorithm is one of them. I'll do them, and the other one is Kruskal's method. So let's do them both.
You want to get rid of the biggest weight, not the smallest weight.
You follow the small.
So we want to have so basically the numbers would be the amount of money you have to spend to connect the two things together.
Cost $1, get 8.
So $1 million or $1,000, pick whatever you get. You feel like
Just a one.
Just 1 unit.
1 rupee.
1 yen.
And so you want to have. So you're trying to minimise the costs.
1 small unit.
Okay.
That got big very quickly.
So Prim's method is pretty much how it works is we ultimately want to get a tree. So a tree is supposed to be connected and acyclic. So pretty much what we do is we just focus it down, we just ignore lots of edges, and we just tick on just 2 edges at the moment. So you start with, find the edge which has the cheapest cost. That's our starting point. AC. And what we're really going to do is we're just considering just those edges, just the vertices connected by that edge. So that's pretty much, our graph really for the moment is connected. We have lots of edges, we're not just lots of points we're excluding for the moment. So how Prim's algorithm works is it starts with not very many points, just 2, and then gradually we add on more and more points, so 1 point at a time. Every time we do it, we make sure that our graph is, or it's always connected that way. Just make sure it's always connected, and we make sure when we add vertices, we don't create cycles. That means it's going to be connected, it's going to be acyclic, so we'll get a spanning tree at the end of the day.
So we have to go to...
So how Prim's algorithm works is, now we've got our starting point, so our starting point is we look at the cost to connect all other points. So basically what we do is we loop through all the edges that leave our little connected bit. So the ones in green so far. So we loop through all of those and we work out which one is the cheapest, which is the cheapest coming out.
A to B.
So A to B, which is a cost of 3. So therefore we then include that vertex and edge. So we're building up a little connected bit. And then what we do next is we look at all edges which are coming out of our new connected part, looking one which is the cheapest available.
Either E and C or F.
So there's 2 choices. So you get ties, what do? Pick one at random.
Oh, okay.
So if you pick them both, you might get a cycle. So you just do one at a time.
But if you pick one, you get a circle.
In this case, it doesn't matter. Sometimes it does.
Go C to F.
So we pick C to F.
No. Oops.
Go.
Actually, no, you get to. And now you got C to E.
So then which is the next cheapest?
F to D.
F to D is the next cheapest.
E to E.
Now, just so before the direct one is to look at, the next one is 4. But before we do that, with this edge here, why would you not? So before you even think about doing the 4, you'd make sure you wouldn't pick that edge I've highlighted in green. Why not? Because it'd be a cycle. So when you're looking at the edges which have the potential, which you're trying to check for to a minimum of, you want to make sure you exclude edges which connect, which basically both ends are in our connected part. So we're looping over all the edges. We want to make sure one of them touches our connected part, one doesn't. They're the only ones we want to consider. If both do, excluded. And that exclusion just makes sure that you don't get cycles happening. Now the other way of doing it is just not cared. Just basically loop through all the edges, pick the smallest. If that happens to create a cycle, at that point in time, you go, oh, forget it. We'll just skip over it and just keep looping through. But as you say, 4 is the next cheapest anyhow. What do you do next? We're done. Why are we done?
All connected.
Okay, so you know you're done when you've managed to connect every single vertex. So you've got all the vertices included. That means we've got our minimal spanning tree. Or a minimal spanning tree, I should say. You may not get a unique answer. There's more than one answer sometimes. What's the cost for this? So it'd be 3 plus 1 plus 4 plus 4
10.
plus 2.
14.
14. Yeah. So 14 million, 14,000, whatever units you want to pick.
Yeah.
$14 is pretty.
So as I said, Prim's algorithm pretty much works is by, if the starting point is just picking the cheapest edge you can find, that's your starting point.
The NBN's so shit.
Because it costs $14.
And then as always, just keeping building up, make sure at every instance, all the vertices you're considering so far are all connected. And then you keep adding the cheapest edge you can to that, making sure there's no cycles ever happening for it. That's basically what the algorithm is. Yes, it will. So it's a greedy algorithm. So it's a greedy algorithm and it's always just choosing the cheapest all the time. Though it's greedy, it actually does give you the correct answer. So it always gives you the optimal solution. Now, sometimes there's not a unique optimal, it'll give you one of the optimal solutions in the case. In this case, that is the unique answer. But in other cases, you might have more than one. Okay. So that's Prim's algorithm. So the other one's Kruskal's, which starts the same sort of way, and you just pick the cheapest edge, which is AC. How Kruskal's works is you don't care about connectedness. Your next edge you pick is just the next cheapest, which would be F to D. That's the next cheapest. So Kruskal's just go, I just always add the next cheapest edge all the time. However, by adding that edge would cause a loop, I discard it. So I just keep always adding the cheapest, just making sure I don't get cycles happening. So you can see I get disconnected stuff right away. So what will be the next one you add?
A to B.
So A to B, yep.
And now the decision happens.
Now you got a choice. So I pick one at random, really.
C.
And C to E.
Drop.
And the next one you pick?
C to F.
C to F. Now in that case, there was no situation where none of the edges we're adding would have created cycles. But if any of those point in time when you're about to add it, you go, oh, that would have created a cycle, you go, no, I'll skip over it, and you just got to consider the next cheapest one instead. So Prim's guarantees the connectedness all the way along, but it doesn't, but there's some edges excluded. Kruskal's doesn't worry about connectedness till the very end. So Kruskal's finishes when everything's connected, as it is here. And so that's all the edges are connected. Everything's connected together, so that's a...
And they both work.
So they both work.
Resulted in the same...
They get the same answer, yeah. The times when these algorithms don't work as intended is if it's a disconnected graph. So a minimal spanning tree only works for a connected graph. If it's not connected in the first place, you can't get a minimal spanning tree. You can get a minimal spanning forest, is okay, and by adapting these algorithms you can discover those sort of things as well. So both of them could work to get spanning forests if you care for it. We'll just stick to the simpler problem though. Your assignment has a minimal spanning tree problem in it. You can pick either algorithm, up to you. And so you really need to set it out to explain all your steps, which I have not done at all here. So I've got the final answer essentially, but I haven't explained what I've done. You need to do in your assignment.
Would you just write that?
I'd be tempted to write, one way to make it really explicit is to go, so for this case, so your first step, that's step 1. Step 2 was that one. Step 3, etc.
Okay.
Just you draw the successive stages of your algorithm.
Okay.
Now, in practice, how you would implement these, we just worry about, I'm just going to assess you on how to do these by hand effectively. So that's all you need to know. If you ever implement them on a computer, there are ways of making it more efficient than what I first presented here. So it does depend on how you represent the data. So in a graph, we mentioned that you can do it by adjacency matrices or adjacency lists. Since you need to loop over all the different edges, it's actually more efficient normally to have adjacency lists. The matrices have to go, you have to loop really through every single entry, even the ones that don't exist, even when edges don't exist. So adjacency lists are more efficient, and then you really want to go through them in order. So you want to have some way of sorting through the edges. And so you need some sort of priority queue is commonly how they do them. And commendation, which is a heap. So binary heaps Fibonacci heaps are some of the different ways of implementing it. Some of these ways people dream up theoretically are very efficient, but they're really hard to code up. So sometimes the one that doesn't look so good on paper, in practice might be better. There's a lot less overhead, much easier to clean the program. But there are different ways of trying to make it more efficient. Because we're doing it all by hand, and you can just see quickly from your eye which is the cheapest. We don't have to worry about any of that fancy stuff, but a computer does. Okay. So another sort of problem is called the maximal flow problem. Let's give it a picture. So this is a way to digraph this time. So it's got arrows, which I hope you can see from there. And so basically we've got 2 points. So you can just imagine these being water flowing through pipes, or in this case how much traffic goes in different directions. This was first applied, I think it was to either traffic or trains, one of the two, in Russia. That's where the first problem was, where they first used this sort of problem. So basically what we're going to do is we want to work out the maximum amount of flow we can have between 2 different points in our neural network. So basically, if this is the amount of maximum, if each of the weights is the maximum amount of traffic you can fit on those roads, what's the maximum amount of traffic you can get from A to B, essentially? So to give you an idea, so from A, we can have at most 8 plus 5 leaving, so you can have at most 13 units of cars going out from A, and you have at most 8 plus 6, 14 coming into B, and so there's only at most 13 leaving, so you can't get the full 14 coming back in, and so the maximum flow has to be 13 or less than that, for example. You can't get anything more coming out from the source. So what I want to do is, well, is it 13? Maybe there's other pipes in there which restrict flow a bit later on. I just can't see that at first glance. What we want to know is we want to work out what the maximum possible flow through this network is. It's called maximal flow that we're trying to find. So we're trying to find the maximal flow of this particular graph. Okay, so the way to do that is called the Ford and Fulkerson's method is a common simple one. Again, these are the guys that came up with the one earlier on, so 50 years ago, that sort of time period. And there's been some improvements to some of the ones, but in terms of what we're doing, this worked quite nicely. So, first thing you do is you're going to relabel all the edges. So we've got our bunch of edges here, and we label the edges with 2 numbers, so it's going to be n/m in general. The first number is how much of the flow we're using so far, and the second number is the maximum amount of flow we can use. So to begin with, we're going to have nothing for the system at all. So we'll have 0/8. So there's no flow, we're not using any flow, the maximum you can possibly have is 8. So we're going to put that everywhere to start with. That's our little bookkeeping. So that just knows how much sort of flow we've got. So that's the first dot one here. The second thing is we're going to do a loop here. So what the loop is, we're going to consider different paths that we might consider through a network. So let's pick on A here. We want to go from A to B on the direction. So pick any direction, I don't care what we're going to do. A to what? A to C. What next?
D.
C to
D.
D.
Then D to B.
D to B. That's a nice easy one to pick from. So that's our first path. Then we look at how much spare capacity there is along each of these different edges. So on this first edge over here, I've got none used of 8. So I'll take the difference between those. So I've got 8 left capacity. So I can fit 8 more cars or whatever it might be on that first one. The next one over here, what's the spare capacity in the second edge?
7.
7. And the last one?
8.
8. So the smallest spare capacity we have is the max we can put on that path, so to speak. So it's going to be 7 in this instance. So that's our starting point. Let's copy it. That's the first case. So basically what we're going to do is we're now going to chuck, use 7 along all that path. So essentially we're just putting 7 cars, so to speak, along that path. That's the most we could fit on that path without breaching capacity. And then we're going to do the same thing, just repeat it over and over again. So what we do now is pick a different path. And we keep going every time we pick a path, work out how much we can push along that to get as much as we possibly can, and keep going until we just can't get any more spec. There's no more spec capacity anywhere. All paths would never get to anything else, and that's the end of the story. And then we can see what the total maximal flow is. That's the basic idea. Let's just run through the rest of it. So we picked the path along the top. We have to pick a different path now.
The bottom.
Sorry.
I'm curious, why couldn't you push 8 through the top
And
bring 1 down at C to E?
that's a different path.
And then
Only from
the third path.
So you can do a different path, A to C to B to F.
But I mean, and include that as well. So push 8 from A to C, and then bring 1 from C to E down, and then A to E. So then you've got the full 13 going through.
Yeah.
So that's what we're going to do, but we do one path at a time. You can see what the next one's going to be. That's okay. But yeah, I mean that's good to see because that's how it's going to work. But we just do one at a time normally. So along the bottom path here, this is another easy one to pick from, and don't worry about your last case. What's the spare capacity on each of those edges down the bottom there? 5, 6, and 6. The smallest of those is 5. So that's the most you can about squeeze through that bottom one there. So therefore we can get 5 along that bottom path. And there's none on these ones over here. So the next thing we need to do is pick another edge where we can get some more capacity out of. And Jacob, you're referring to one. So one is, I can't go for any more from A to E, that's completely full. So the only thing left is A to C. And it's just said, the only one possible direction I have to go to C to E. We have to go to E to F.
You have a choice.
And you have a choice. Let's pick the quickest way. Let's go to E to F to D, F to B, for example. What's the spare capacity in each of those edges? What's the spare capacity on A to C?
It's going to be 0 then. So you're going to have 8. It's got 1 left.
1 left. So it's got 1 spare capacity. What's the spare capacity from C to E? 4. Spare capacity from E to F? 1. Spare capacity from F to B? So the smallest of those numbers is 1. That's the most you can squeeze through. And so the last thing to do would be to push 1 unit along that particular path to fill up all those. And the next thing you do is try to find another path to try to put more through. But you can't. Why can't you get another path?
There's no more output from A.
Yeah, so A, if you look at A, it's pushed everything it possibly can. It's completely, there's no spare capacity coming from A at all, therefore you really have to stop at that point in time. So at the end. So what is the maximal flow? What's the most you can push out of A and into B?
13.
13. So it's 8 plus 5 equals 13. So just recapping how that worked is we started by putting, so just changing what all the labels of the edges were. The first number is 0 to say we're not using anything yet. A vertical line to say how much is left. Picking one path at a time and just working out the total amount we can push along that, just determined by the smallest capacity of any of those edges. Just add that to each of those different edges and then just try different more paths. And keep going until you run out of paths that would work. And then once you've got that, that gives you one way of getting maximal flow through the system, and that would work maximal flow from that. There may not be a unique answer, and then the actual flow is unique, but there may be more than one way of getting that maximal flow through the system though. As you remarked here, that last path, instead of going from F to B, we could have gone from F to D to B, but also have worked. There's more than one way of getting it through. Just some other comments about this algorithm. We can put cut lines through here. Just want to cut the graph at various points in time. This is called a cut. So a cut is basically putting a line which doesn't pass through any vertices. And looking at how much flow is possible through that. That'll make it easier for just the clean graph. So if I cut through here, what's the total amount of, the maximum amount of flow I could get through from the left to right? Well, there's an arrow here. So the most would be both of those completely full. So 8 plus 5 gives me 13. So the maximum I get through that cut is 13. If I pick this cut over here, what's the maximum I can get through that cut?
13.
14. You pick other sorts of ones as well. So if you pick that cut there, for example, what's the maximum you can get through that cut?
16.
So it'd be 7 plus 4 plus 5 gives you 16, as you're correct. You just pick one more. So pick this one here, for example. So 7 plus 4 will be 17. So different cuts give you different values. So the smallest value you'd get from any cut, which is 13 in this case, is equal to the maximal flow. So they're sort of related to each other. So the minimum cut is equal to the maximum flow. And so they're sort of related. So coming back to this sort of problem here, you can work out what the minimum cut is by looking at what you've got here. You look at all the different edges which have no capacity left. So you can see that one has no capacity, that's not no capacity, that's got no capacity, that one is. So those edges all have no capacity left. So any line passing through those would give the minimal cut. And so the only one that makes sense is the one I've actually drawn in blue there. So if you wanted to increase the total flow through this network, the bottleneck is that cut point. That's really what it is. So that blue line there really is our whole bottleneck to the system. So if you wanted to improve flow, we'd have to fix that bottleneck up. And so by basically going from A to C, if you may increase the capacity, I widen the road or whatever it might be, to make it 9 rather than 8, you could get more flow through the system. Whereas if you increased, B to D going around, it doesn't help at all, because that's not the bottleneck. So this minimal cut idea is useful to identify where bottlenecks are, and therefore helps you think about how to increase the flow even further. And as I said, how you work them out in practice is you work at maximal flow just like you did there. Look at all the edges which have no spare capacity, and if you can have an edge which joins lots that can pass through all of them, that would be a minimal cut. And that identifies key edges. You might have more than one of them. So if all minimal cuts pass through one edge, that's your guilty point. That's where your bottleneck is, for example. So some useful sort of things you can see as a sort of after post hoc analysis you can do for these sort of things. No, I didn't quite very nice. nicely. So this is something in the middle of stuff. So this is another graph. We're not going, we work a flow from A to B. You can see I've gone through most of it already. Let's try to get another path that can squeeze a bit more out. So we're starting at A. Where would you go next?
To D.
To D. That's the only choice we've got. Next.
To C.
So I go to C. And then it looks like we're stuck. If you're not, I don't know if you can see, but the arrowheads are here and here. So from the edge from C to B is completely full, so we can't use that one. The arrow from C to E is pointing in the wrong direction. So it appears that we're stuck and we can't do anything more. Not quite true. We actually have used, got cars, whatever it might be, 2 units in that direction. So what we can do, as long as there is actual capacity there, we can subtract some of that off, going in the opposite direction. So we actually can use an edge. This is the one that's special. We're using an edge in the opposite direction. And then from here,
of the road. Driving on the wrong side of the road.
Basically, we're in India.
There's only 2 cars there, so it's okay.
It's subtracting from a flow that we've already used before, essentially. So one way of thinking of it. So what's the spare capacity in each of them? So the spare capacity here is 1. 4, 1, so they're easy ones to do. The edge that we're going after is blue. What's the spare capacity that we can use in the direction from C to E?
3.
And from the other way, if you want to go from A to C, there's 3 left to go, but we go in the opposite direction. So we can subtract off at most 2, and still everything works out okay. So our spare capacity in the opposite direction is the 2. That's the funny thing. So we start it again. We want to go opposite. So the only way of going opposite really is to subtract off what we already have. We have 2 already. So the most we can pull away is just 2. That's the only thing we can pull off.
Basically, they just screwed up the graph earlier. I'll fix it again.
So you could do the whole thing again by just rewinding a bit and go, okay, I'll just deduct the whole path just to give them a bit of room and then add a new path in and be all okay. So you can avoid it if you wanted to, but sometimes you're just going full ahead. You go, oh, it's already there. I don't really want to backtrack. I'll just run a path backwards and it's okay.
When we missed the exit, we got to just drive backwards.
So if the spare capacity on that edge in the direction we're going is 2, the minimal, what's the smallest of those spare capacities? What's the smallest of 1, 4, 2 and 1? 1. So therefore we can fit 1 more along that edge. So that would be 9, that'd be 1, that'd be 7. What does that 2 become? 1. So we're reducing it by 1.
What?
Why would you think it becomes 4?
Yeah, well, I was thinking just double it, so you got 2 back. There you go.
So
That way it's 2 proper highway, 2 each way, you know?
So we subtract.
I don't know what you're on, but...
So how we work in this case is we want to increase the flow in this direction by 1. That's the opposite of what we want. So in terms of the direction we've got, it's actually -1. And so we have to do -1 plus our 2 to give you 1.
What? What? So by subtracting 1, I'm now Jesus.
That's not how it works at all.
Yeah, well that's not logical either.
It's the performance of all the triples. Just pour some water into that wine, you get more wine.
You do, but it's not very good wine.
Turn water into wine.
Okay.
We're putting the fire into the water.
I can see people are convinced. So how would I do it completely differently? So that's the quickest way of doing it.
Now for something completely different.
The problem we've got here is we want to go from A to D, but both D and E
and C to B here are full, and that's our problem. And so what we need to do is just rearrange some stuff. So one way is to use the trick of using just having a negative flow essentially. That's what I really did. Where you go, look, I just need to take some pathways just to get the space in the right area and then fix it up. So one sort of problem was
You can't just push shit back through a pipe and hope for the best. It doesn't work like that.
it's shorthand for this, what I'm doing here. So that's one possible path,
Doesn't care.
which goes along the place
That's
where...
the problem, Dave, is that maths doesn't care.
So D to E and C to B here are the ones that are full that really are stopping us from getting that other path in. So what I'm going to do is I'm just going to subtract one along that path just to go backwards. I'm really backtracking at this point in time. And that's just going to create some space. So I'm going to reduce this to 7, that's 1, and 6, just subtracting 1 off along the whole way, just to create some space for me. So the problem really with this case is I was just a bit too gung-ho along that particular path and filled things up when I really didn't need to. Is one way of looking at it. So I just, and so now I'm going to go back to what I normally do is I'm going to try to find paths to put some flow on. And now I can see, look, oh well, okay, I can just go around the the bottom here. So, let me do that. So that was 7, now that's up to 8 again. That's back up to 8 again. And that's 7 now, isn't it?
Makes sense.
Yeah, so just all I'm doing is just adding 1 along to the bottom, because why? That's the minimal spare capacity. So the spare capacity is 2, 1 and 1, it's just adding 1 to all of it. That's my new graph. And then I'll just try to squeeze 1 more path in. And the new path is going from A to D, to C, along to B. That's another path which has spare capacity along the whole way. What's the minimal spare capacity along that particular path? 1. And if I could put 1 along on that graph. So that'd become 9, that'd be 1, and that'd be 7. And that's still the one from earlier. And if you compare that graph there to this one, it's the same. So what I've really done is I've realised I got stuck. So one way is just to allow for negative flow just in the interim, which is what I've done. Or the longer way is to go, look, I've just gone too far, I just need to pull back, I just need to subtract 1 whole path out, just to give my space, and then go forward as per normal. But by doing the slick method of just applying subtracted flow, you can actually do it the whole thing much quicker. It's shorthand for the longer method though. And the only reason why I'm allowed to do that is because I had some flow, namely 2 there already I could subtract from. If it was 0, I couldn't do it. So equals actually has something to subtract from. Just like here, when I was on the screen method here, I was subtracting 1 off. I could only subtract 1 off because there's already something in that system. That's the only reason I could go backwards, essentially. So it's an advanced technique, and you can see I didn't actually have to use it in that first example. And so in your assignment, and possibly in your exam, you're going to have a maximal flow question. You may or may not have that trickier case present. Depends how you do it, admittedly. So I may not intend it to be there, and you may create it for yourself, depending on choose path. So if you get stuck, one is to use the fancy negative. If you really dislike that, which I can tell some people don't, then just go, okay, I just got to backtrack and just start again, effectively. Try different paths to begin with to avoid that problem. Okay.
So if one of these are in the exams, we need to show step by step in that too or not?
Yep.
Oh.
always like disappointed.
So there is one of these in the exam.
There are. So you've basically the exam's 5 questions.
So just like the last one, there was 3 questions, but each question had like 27 different parts in it.
Yeah. So same idea. And so the
HSC, there were 6 questions.
there's one question on graphs and trees and weighted graphs. So there will be some question on weighted graphs in there. So one of the algorithms we talked about this last hour. I probably can't put them all in your exam unless you. It's only a 3-hour exam after all. So I can't do them all. So you'll probably get 1 or 2 at most. Probably. I have written it. I can't remember.
Did you just say it's only a 3-hour exam?
Yeah, that's not that bad. At least it's not 7 hours. That would be horrible.
I don't even think that'd be legal. Like you'd have to give us at least a half-hour break, just like when you're working. If you work more than 5 hours, and you have a half-hour break.
Intermissions for a few drinks, you know.
I
Snack.
It's like I'm gonna need a cider after that.
If someone walks around with water.
I presume what has to happen. I've never explored it. I would presume you have to give more than one paper. Give you 2 separate papers or something if I want to make it any longer than that.
Can you just give us an exam that's like 15 hours long and see what happens? Just to weed out the weeks, people. Only the strong make it the whole 15 hours.
One kid who snuck like 17 cans of Red Bull and goes, I can do it.
He's like,
I can do it.
What's the last question?
At the end of the day, I just want to know if you can do the material. I don't think I need 15 hours to work that out. Like you normally, if you don't know it at all, you probably show your colours in a much shorter time period. And if you know it really well, you can also show your colours quite well too.
Which subjects?
Which
courses?
The last algorithm I want to look at is the shortest path. So here's our graph, same one as before.
Marketing and advertising.
Okay. For the sake of time, I'll just do my slides for this bit in a second. So this, I want to work out the shortest path between A and B and D, for example. So path finding algorithms is pretty useful. So you've got a robot, and you want to get the robot to pick the shortest path from here to somewhere else.
I don't want the robot to leave. I've got a robot.
He passes the butter.
The whole idea of you want to use get the robot to, take your food from here to someone else.
Passing the butter.
That's what
he does.
So why doesn't it just go straight there rather than go?
Well,
Yeah, he just goes straight over to C.
That's my robot.
Why can't it go B to C? Why does it have to go B A C or B?
Well, because
to
there's
C?
stairs, and robots can't go upstairs.
So here's a robot. Here's a table.
How does it get from A to A?
And this is the sofa,
B to C.
which is in the way.
What about B to E?
And so,
An escalator or something.
this is what you really do for a robot problem, is that basically you have lots and lots of nodes. Nice grid pattern, much neater than what I've got.
When you turn on that robot that vacuums your floor, for the first 17 weeks, it's just navigating around finding what there is, and then it starts cleaning.
So every 7-10 weeks you should move your furniture around just to mess with it.
Why don't that long?
So basically,
we're going to get a clean floor.
So how a path finding algorithm would basically have lots of nodes, and it basically works out the distance. And how I'm going to work it out here too is the same idea. Is I'm just going to look at the nodes closest to it and work out the distance by these different nodes. And what will happen is it just go normally. Normally you just go diagonally is the quickest. You hit the sofa in the way, you get the sofas in the way.
That's where the chainsaw comes in.
It's like a gauntlet.
And the shortest path is probably more like that. That's probably more the shortest path, which just skips around the sofa.
Can you get under the sofa?
Well, it depends on your robot. It's one cousin, but
Doesn't really.
so
It also, yeah, that's it.
so a robot
This is the whole.
trying to drive around a room has in order to get the shortest path more accurately needs lots more nodes. But the process is the same as much simpler one.
Next step was to
Let's do a simple one. So
It's in the middle and gets confused.
I called using Distra's algorithm. I'm having trouble pronouncing his name. Anyone want to go at it?
I'm just going to call him Dijkstra.
I don't know.
Let's just call him the dude who did the Roombas.
Okay. So basically, how I'll do the first. So how it goes is, you want to label all the vertices with a distance from B, and we're going to do it gradually. So for the moment, to start off with, you put the distance from B to B is 0. Okay, we know that one. That's the easy one to do. Everything else we don't know yet. So you put a tentative distance down on all the other ones, and since we don't really know, it's going to put infinity. So
There's no getting that. It's infinite distance.
yeah, so we don't really know what the distance is, so we have to put a tentative value down. So our tentative value is infinity for the moment, because that means we have really no idea yet. So that's the first step. So then you do the loop. So in every part of the loop, you find the... so what we go is we process through the algorithm, we colour some nodes in. We haven't done that yet. So as you're going through the loop, you find the node, which is not coloured in, which has the smallest tentative distance. Which one's got the smallest tentative distance so far?
B.
B. It's the only one that's got a value. So what we do is we colour it in. So we colour it in. Blue in this case, just to make it easy to see. And then from that, we work out the distance to all its adjacent nodes, which haven't been coloured in yet. So we go from B up to A, and the distance along that's 3. So now the new tentative distance from A to B is 3 this time. Not infinity anymore, we've got a bit of a better estimate. And from B to E, go along its path would be a distance of 6. And we put that value on the node. That's the shortest distance we know of so far. And then we repeat. So the repeating idea is to go, okay, now of all the nodes we haven't coloured in yet, which has the smallest tentative distance for it?
A.
A. So A is 3, E is 6, everything else infinity. So A being 3, certainly the smallest value. So what we do is we colour that node in, which essentially is say we've visited. So colouring just, another way of saying it, that's a visited node. So we've coloured that in, and then we repeat the process. So therefore we look at the numbers going along all the edges. So from A to C we've got one more distance, plus the 3 we've already got from getting to A in the first place. So 3 plus 1 would be 4. So the shortest distance from A to C would, from B via A to C would be 3 plus 1 gives you a total of 4. If you go down from B by A to E, it would be 3 plus 6, that'd be 9. But we already have a value of 6 there, which is better, 6 or 9?
Probably 6.
6, so therefore we leave it at 6. So we actually already have a smaller value, so we'll leave the smaller value. So we haven't worked another one, we go, no, we'll leave that behind. And they're the only paths we have to consider. And then repeat. So we look at all the different nodes that haven't been coloured in, so 4, 6, infinity, infinity, which is smallest?
C.
So C is. And so we colour that one in. And then we do the same thing again. Work out, so to get to C it has a distance of 4. So go to from C to D, it's 4 plus the 5 gives you a distance of 9. So it was infinity before because we had no idea. Now our best estimate's 9. Now it could be a bit low, it could be lower than that still, but it's only at most 9. Then from 4 down to F would be 4 plus this 4 here, so it'll give you 8 going down here.
Wouldn't E be 8? Wouldn't E be 8, not 5?
No, because you got to E.
So C is...
Yeah, because you...
I forgot to change the rule. There you go. I meant to change things to what? Or 1. There you go.
What?
The 4 is supposed
What?
to be 1.
Ah.
Let's just...
Alas, that makes more sense.
I try to change things to make it a bit more informative. And I changed one part and not the other. Okay. So, what I meant to do is I meant to change the problem magnitude to 1 rather than 4. Just to illustrate some of the things that happen. And I didn't change my labels very well, so sorry about that. So to go from the distance to C is 4, so going along this edge would be 4 plus 1, what we had before. So the value of the value of E was used to be 6. It was 6 before. So it was 6. So it was 6. Now if you do it this way, it's 4 plus 1. That's the new method. So it was 6 by the old method. Now it's 4 plus 1. Which is smaller of those two?
5.
It's 4 plus 1 is 5. So therefore we delete the 6 we had before and put the newer value of 5 down. So what I want to show you, as you're going through the algorithm, you need to sometimes update these tentative distances. So let's just make it maybe clearer. So from the past step, it would have had a 6. The label on that edge was 6. That's the shortest distance we know of so far to get to E. So what we've realised though is if you're going from B to A to C and then down to E again, the distance would be 4 plus 1, which is 5. So by a new route, we've actually worked out there's a shorter path still to get to E than there was before. So we delete the old one. And you go, well, it really isn't. 6 is not the best, but I can actually do better than that. I can do 5. So that number shows you just the tentative distance, the tentative shortest distance.
I'll give you 6. Best I can do is 5.
So it just shows you the best we know of so far, the shortest distance so far to get to that particular node. So as you're processing, you might find a shorter path still. You need to update it. You need to check it as you're going along.
Good to see.
So then at that point in time, you then look at the nodes, work out which is the cheapest. So 5 is the cheapest. You colour that one in and do the same process. So from 5, the distance to E is 5, distance plus 8